so 11.4, you have to think this is the pre-calc honors book, right? We're back to that. So the language changes a little bit. This is limits of infinity and limits of sequences, okay? Limits of infinity basically mean end behavior. That's what this, it's the same thing. So this, in these situations, you're going to use the limit notation to describe the behavior of the graph as x approaches infinity and negative infinity. In other words, all the way left and all the way right, which is the end behavior. So all the rules that applied to end behavior apply to today, okay, with one exception. So when we describe this, the first thing I would look at is if I had a graph, if I want to know the limit as x approaches negative infinity here, okay, look all the way to the left. What's going to continue to happen as I move this curve to the left? It goes to the horizontal asymptote, which in this case is 1/2. So nothing changes here. We would say the limit of the graph as it approaches negative infinity is 1/2. And then as I'm going to the right and I'm going to positive infinity, what's the limit of my graph? 1/2. Also the horizontal asymptote. So if your function has a horizontal asymptote, then the horizontal asymptote is the end behavior. That is nothing new, okay? What changes, so that is all the thing on the bottom, okay? The horizontal asymptotes, if the exponent in the top is less than the bottom, then the horizontal asymptote is at 0, which means your limit is at 0. If the exponent in the top is the same as the bottom, then it's the leading coefficients, then that is also your limit. Here's the difference. Where we would have said it goes on, so if it didn't have a horizontal asymptote before, do you remember what you did? If it didn't have a horizontal asymptote, we like plugged in infinity and we plugged in negative infinity, right? Because we're not talking about the limit of the graph, we're talking about the behavior of the graph, and f of x was going on to infinity or negative infinity. Now you're saying the limit is where does your graph stop? So if it's going on to positive infinity or negative infinity, where does your graph stop? Never. It never stops, which means the limit does not exist. So instead of saying our end behavior is infinity or negative infinity, we sub in does not exist, okay? Because you're talking about a limit instead of the graph itself. The graph itself continues on forever, but the limit of that graph would not exist. That is really the only change on this part, okay? So we're going to use the horizontal asymptote. We're going to find the horizontal asymptote. If there is no horizontal asymptote, then we say the limit does not exist. That's the only difference, okay? All right, so look at example 2. Find the limit, and this time it's just saying as it approaches infinity, but it could also say negative infinity. It could say either one. And again, if it does not exist, we're going to do D and E. So what's true about the exponents in A?
It's bigger than 9.
Good. So top is smaller than bottom, which means where's my horizontal asymptote? 0, which means my limit is 0. Go to B. What's true about your exponents?
They're equal.
They're the same. So how do I get the horizontal asymptote this time?
You put them over each other.
Good. Leading coefficient. So 2 over negative 1 would be negative 2. Because that's a 1 on the front of that x.
Isn't it 1, like the leading coefficient?
No, leading coefficient's the 1 on the front of the highest exponent, of the term with the highest exponent. We still good? Okay, example 3. Now this is what the limit notation would look like, and it means this, okay? Those two can be used interchangeable. So you'll either say the words, find the limit as x approaches theta, or it will literally say limit as x approaches theta, and it means the same thing. This is end behavior. What's true about the exponents in C?
The top's bigger.
Top's bigger, what happens there?
0.
If it's, no, top's bigger, what happens?
0, right?
Mm-mm. It doesn't exist.
Slant.
Oh, slant? Are you saying slant? If it's 1 bigger, there's a slant. Yeah, but really the limit just would not exist. Yeah,
So if there's a slant, oh, I'm switching.
correct. You're switching it in your head. Yeah,
Yeah.
you're not an idiot. All right, D, those are separate terms. So before I can figure out what the exponent relationship is, we're going to make these the same terms. We're going to give them a like denominator. In this case, it would just be x squared. And I'd get 4 plus 3x squared over x squared. Now, what's the relationship of my exponents? They're the same, so the leading coefficients would be?
3.
Good, 3 over 1, which is 3. Right? Take back all your whining. No, because it's the leading coefficient. We go back to horizontal asymptote rules.
And they're equal.
All right, the second part of this is using sequences, okay? Now, if you remember your sequences, these could be arithmetic, they could be geometric, they could be all the things. Here's the good news. It is exactly the same rule, except that you will have an n instead of an x. So it will say something like an equals n plus 3 over n minus 5, let's say. That is a sequence. When it says find the first 5 terms of the sequence, you would do what?
1, 2, 3.
Plug in 1, plug in 2, plug in 3, plug in 4, plug in 5, okay? If it says what would be the bound, or it would say as n increases without bound, what happens here, find the limit of this function or this series, you would literally go back to your rules on your exponents. So the exponent on a and n is what we're looking at this time. They are the same, so this would be a leading coefficient, and it would be 1 over 1, and the limit of this graph is 1. What this means, like language-wise, is that the sequence is said to converge to that value. So whatever the limit is, we say that the sequent converges to that limit, which means it's going to get closer and closer with never actually hitting it, because it's like a horizontal asymptote. And that's all you're looking for. So you're looking for exactly the same thing. Different language, same thing. In this case, and we won't do the first 5 terms on B, we'll just do it on A because we know how to do it. But it says find the first 5 terms in the sequence and use the terms to evaluate the limit of the sequence. Now I use it in reverse. I find the limit and then I find the first 5 terms. And the terms, the pattern on the terms confirm your limit. So if I look at A, what's true about the relationship of the exponents? They're the same, which means this is the leading coefficient scenario, and my limit would be what? 2. Now I'm going to plug in my values. So I'm going to do 2 times 1 plus 1 over 2 plus 4. And then I'm going to do 2 times 2 plus 1 over, why did I do 2 the first time? Sorry, that should be 1. 1 plus 4. This is 2 plus 4. Then I'm going to do 2 times 3 plus 1 over 3 plus 4. Then I'm going to do 4. And then I'm going to do 5. So it's tedious, but we know this process. This would be 2 plus 1 or 3 over 4 plus 1, which is 5. This is 4 plus 1 or 5 over 2 plus 4, which is 6. This is 6 plus 1, which is 7 over 3 plus 4, which is 7, and that's 1. This is 8 plus 1, which is 9 over 8. And this is 10 plus 1, which is 11 over 9. So notice what's happening to these values. These fractions are getting bigger. They actually surpass 1. So if I had said my limit was 1, I would know I did something wrong. Okay? They surpass 1. They are getting bigger. And if I continued to enter in numbers, I would keep getting closer to 2, and I would never actually hit 2. Okay? So that's what it means by, like, use the terms to evaluate the limit. I use the terms just to check the limit. You should be able to find the limit already. So go to B. What's the limit there? 0. If you plug in your 1, 2, 3, 4, 5, your values are going to get smaller, 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 but never hit 0. Yeah. If you plug in, not necessarily, because direct substitution should give it to you. No, but it's not asking for the limit at 2. It's asking for the limit at infinity. Yeah. If it said limit at 2, then you'd plug in 2. And that it equals your limit. Yeah. But in this case, this is like these words mean the same thing as find a limit as n approaches infinity. Yep. We're good, yes? Questions? That's it, people. So this does not mean you just yell 4, okay? This is called a factorial. A factorial says you multiply this number times 1 less, times 1 less, times 1 less, till you get to 1. So this is 4 times 3 times 2 times 1. Okay, technically you don't need the 1 because it doesn't change it. That's what a factorial is. That's what it means. So on the homework you get something like n. Well, let me show you a trick. Let's say I have a fraction. Shh, guys. Shh. Let's say I have a fraction that says this. Okay. Well, you want to break it down until it cancels. So 11 factorial over 9 factorial. I pick whichever one is bigger. So 11. And I break it down until it hits the smaller one. So instead of multiplying 10 times 11 times 12, times 9 and all the way down, I do 11 times 10 times 9 factorial over 9 factorial. And then these cancel. And this answer is just 11 times 10. So you're going to have to do that with variables because there's a question that says that. So let's say I have n plus 2 factorial over n factorial. Which of those is bigger? N plus 2, right? So if I break that one down, what is 1 less than n plus 2? N plus 1, right? What is 1 less than n plus 1? N. And now they've hit the same, and I cancel them, and I would multiply those out. Okay? So yours, I think, is n or n plus 1. Just break that down until it gets to the smaller one. Yep.